and then start with our introduction. Awesome. Welcome, everyone. Good morning. It's really amazing to host Gagan Bansal. So Gagan is actually did his PhD at UW with Dan Weld, who's also in the audience. So it's a pleasure to have him, give this talk to the UW, largely a UW audience. So Gagan is a researcher at Microsoft Research. He's part of the AI Frontiers group, co-leads the AutoGen framework for building human multi-agent AI systems. And his work lies at the intersection of AI, HCI, with a focus on making AI systems more capable, interactive, and useful to people, something we all really need. And he's also been a driving force behind several open source agentic projects, including AutoGen, Magentic-One, Marketdown, and he's going to talk about some of the concrete problems for developing some of these human-centered agents. With that, I will pass it over to Gagan.
Yeah, thank you. Thank you so much for inviting me. So yeah, as Tony said, I'm a researcher at Microsoft Research AI Frontiers. And today what I'll basically do is share some of my perspectives on what I think are some concrete problems for developing human-centered agents. Um, and I've been at Microsoft for about 3 years now, 3.5. But since the last year and a half, we've actually created this new lab called AI Frontiers. This is a new lab inside Microsoft Research, which means that we work on a small number of high-yield bets. And we're also cross-location, so we have people spread out through offices in Redmond and New York and Montreal and Silicon Valley. And there are three big themes that labs are working on. One is model training, the second is agents, and the third is evaluation of these technologies. And here are some popular projects that you might have seen from our lab. So Phi and Orca on the left are the state-of-the-art small language models. These are language models that have achieved high performance relative to their size. And in the middle is AutoGen. This is a framework for building agentic applications. It's especially useful for building multi-agent applications. And on the far right is Eureka. This is a framework for evaluating large language models. And in this talk, I'll mostly focus on our experience building applications with AutoGen and building that framework and providing a more HCI perspective on the learnings through this process. And although I'm presenting, most of the work that I will talk about today was done in collaboration with our core team and interns and many internal and external collaborators, some of those who are present here as well. And our core team is actually pretty full stack. We have folks with experience in systems research and machine learning and human-computer interaction. Some of them are designers, some of them are program managers. And so diving into this talk, my current sort of high-level perspective is that we should be developing human-centered agents. And to enable it, there are at least three problems that we should be thinking about. The first problem is effective task completion. The second is maintaining common ground between people and agents. And the third is auditing behaviors of agents. And before I go into details of these three problems, what they are, what we can do about them, let's try to get on the same page about what we mean by the term agents here. The term agents is very broad and it could mean many things. And I'm sure like most people in this room have a definition of agents that they prefer. I belong to the bucket of people who really like the definition from the textbook on Intro to AI by Russell and Norvig, specifically from its chapter 2 on intelligent agents. And there, Russell and Norvig define agents as entities that contain action and perception loops. What this means is that the agents perceive the environment through their sensors, and then they use their actuators to act. And these actions can change the environment. And the goal-based and the model-based agents defined in this chapter are especially relevant. What's different here is that these agents maintain beliefs about the state of the world or the progress on the goal or the state of the goal, and then use these beliefs to reason and take those actions that help achieve those goals. Now, if you look at this book has existed for almost 3 decades now. But people are saying 2025 is the year of the agent. So why is it the case that agents have become so popular now, so ubiquitous now? What has changed? And I think one big change that has happened is that we've generated models now. And these models have made it significantly easier to connect perception and action. They've made it significantly easier to reason about the environment and the observations and the goals and take appropriate actions. And I think the second big change that happened and actually was pretty clever, these models again have become really good at using tools. In fact, they're optimized for tool use. And tool use, again, further helps create these productive action perception loops. So in other words, I think what has really changed is that these new advances have made it easier to implement these goal-based and model-based agents that Russell and Norvig were talking about. And these agents are having real impact. One of the things that differentiates these agents from chatbots is they can actually do things. So like think of a personal assistant that can not just give you advice about what you should do today, but actually can handle those tasks for you. Um, and while these changes have made it easier to create these powerful goal-based agents, they've also created new concerns. So for example, these agents can have vast action spaces. The number of ways they can impact the environment can be quite large. So for example, think about an agent that can write arbitrary Python code and execute it. This agent can impact the environment in so many ways. And we'll talk about some of these things later in the talk. And to achieve these goals, these agents might use a multi-step reasoning and action. This process can get very complex and become unintelligible to users. And finally, we know that these generative models can be quite stochastic. This is one of the fundamental issues with these models. And so what can happen is that these agents can fail in very creative ways and troubling ways. And when the stakes are high, in domains like healthcare or whatever you have, this can become quite unacceptable. So a lot of new concerns have come up, even though, or become, existing concerns have become more challenging with these new advances. So then the question then becomes is that how do we go forward? How do we, head into a place where we're creating useful user-facing agents? And I think this is where this thinking about human-centeredness of solutions, human-centeredness of agents, this is where I think this comes in. And what I'll try to convince you on the rest of this presentation is why these particular problems deserve our attention, what exactly do I mean by them, and some of the progress we've made in trying to address them. So let me first actually provide you with examples of these problems before we dive deep into them and some of the progress in each of these categories. So let's, for example, consider the problem of effective task completion. What I'm going to show you next is a demo of the Magentic-One system. This is a system that we released last fall. It's an open source system that's available, and it's a generalist agent for solving complex tasks. What you're going to see next is a demo of Magentic-One's command line interface. It's super easy to install. It's open source. And what I'm going to do is ask it this complex intent, which is, I'm going to Kai 2025. Can you find me Indian places that have vegetarian foods near it? Please keep your responses in English. Now, if as a person I needed to solve this particular task, the first thing I need to know is where the heck is Kai 2025? And then I need to figure out where the closest restaurants to it that fits the user's preferences. So now let's see what this agent will do, what Magentic-One will do. Okay, so the first thing it's doing is that it took the user's intent and is trying to create a plan. It's trying to think about what the known facts are, what the agents that it has access to, and then it's trying to create a plan. And then what it does, it starts to actually operate a web browser. It's looking at where Kai 2025 is, figures out it is in Pacific Yokohama. And now it starts to look up for vegetarian restaurants near Pacific Yokohama. And then it tries to, answer that query. And it found a bunch of restaurants. And actually, while I was attending Kai, I actually went to some of these restaurants and they were quite good. So this challenge of task completion is really about whether the agents can correctly solve the task in a timely manner while minimizing costs. Okay. So let's not talk about the second problem, which is about maintaining common ground. And what I'm going to show you next are two demos, one from OpenAI's deep research and another from a new browser use prototype that we recently developed and released. Here I'm going to ask the deep research from OpenAI a similar question to what I asked Magentic-One just now. So again, saying, I'm going to guide 2025. Can you please find me vegetarian restaurants near it? And notice the first thing that the system does. The first thing the system does is says, can you please just share a little bit more about the details of what you mean? It's asking, is there a specific kind of vegetarian cuisine that you like? Do you have a price range in mind? Do you have a dining takeout? So it's really trying to understand what the goal is before it invests all these GPU cycles trying to answer that intent. And this also speaks to the complexity of specifying complex or the difficulty of specifying these complex intent. People are not good at specifying the goal in natural language completely. It's hard to do that. Okay, here's another demo this is from the Magentic UI system. Here I'm going to ask a similar question and notice what this one does. Again, asking the same query, I'm going to Kai, can you find Indian restaurants, vegetarian food? So this system instead now presents a plan to solve this task. And it gives the user the option to actually edit that plan. So it's trying to get on the same page about the process of achieving this goal. And once the user accepts that plan, it starts to go ahead and execute on it. So again, it's trying to use a browser, it's trying to look up, the location, and then it finally finishes the task. And actually, this space of maintaining common ground between people and users is actually quite complex. And in the later part of the talk, I'll talk about how rich this really is. Talk about some concrete problems, sub-problems in this space. Okay, now let's quickly focus on the third problem. And here's a motivating example for auditing agent behavior. So what I'm going to show you here is a log generated by one of, again, these systems when it was given a task from the Gaia data set. This is a very complicated task. Nobody in their right mind would ever try to do this task, but it's one of the challenge problems in the Gaia data set from Meta. And now let's look at the log of the exception perception loop that the system generates. So this is a text file of the log that I've opened up, and just look at how dense this is and how long this is. How the heck do you figure out what went wrong or right in this particular log? And the reason it's so long is because agents pursue these multi-step complex plans. Okay, so the three problems that I'm going to talk about is, can the agents finish the task? Are they able to effectively communicate with the users? And are they doing anything to keep that communication effective? And finally, how do we find issues in these agents and how do we fix them? Okay, let me first start talking about the effective task completion problem. And here I'll talk about our recent work on Magentic-One. So Magentic-One is what we call as a generalist multi-agent system for solving complex tasks. And there are three keywords here that really stick out. The first one is generalist, the second is multi-agent, and the third is complex tasks. So what the heck do I mean by these? The reason Magentic-One is a multi-agent system is because it contains 5 agents: an orchestrator, a coder, a computer terminal, a web server, and a file server. So the orchestrator is this agent that can plan, can track progress, and coordinate the other agents. Whereas the coding agent can write Python and shell code to solve tasks, the computer terminal can execute it, the web server can operate a stateful web browser. It has the ability to quick scroll type on web pages. And then the file server similarly can navigate files like PowerPoint files or PDF files and even audio files. And the reason we call Magentic-One a generalist agent for solving complex tasks is because it's able to actually pursue a lot of different kinds of problems. So here at the bottom, what you're seeing are 3 tasks that belong to different domains. But the common thing about these domains is that they all require multi-step planning and execution to solve these tasks. And none of these can be solved with just a single LLM call or without tool use. So let's look at what Magentic-One does in some of these scenarios. So the task here is to count the number of members of the MSR hacks team. This is the team I'm part of. Okay, so again, it gets a query. First thing, like we saw before, is creates a plan. This time it's also creating a ledger. It's trying to think about, is the request satisfied? Is the progress being made? Starts to operate the web browser, reflects on, again, is the progress being made or are we done yet? Continues to do this loop until it finds the right answer. So in this case, it's found the page of our team. And now it'll eventually count this and arrive at the right answer. And so it says the MSR hacks team has 7 members listed on an official base. And this time it was using the web agent quite a bit to do this. It's a different task. Again, the very same Magentic-One system, describe trends in S&P 500. In this case, again, it creates a plan, but what we'll notice is a difference. This time, instead of choosing the web server, it's picking up the coder and asking it to write code to analyze the trends in S&P 500. So it's using Python, installing libraries to get the data, and then analyze it, and summarize it, and figure out the trends. And if you ran the system again on the same intent multiple times, like we talked about, stochasticity of these agents is a problem, it might behave differently. For example, here's another task from the Gaia dataset. And the question here is, of the cities within the United States where presidents were born, which two are the farthest apart from the westernmost to the easternmost going east? So if you gave Magentic-One this particular task, what you're seeing here are 3 different plans that it might use. In the leftmost plan, it goes to Wikipedia, it finds a list of presidents of the United States, and it chooses the scroll action to scroll on that web page, maybe scrolls multiple times, and then uses its internal knowledge to figure out the coordinates of the cities where they were born. In the plan 2, it again goes to Wikipedia, but instead clicks on the birthplaces of each president, and then searches the web for the coordinates of those birthplaces. And the third plan, it doesn't go to Wikipedia. Instead, it goes to this other website called presidentusa.net, views their birthplaces to collect the data, and instead this time starts using the coding agent, installs the GeoPy library to get the coordinates, and run this Python script. Okay. So how does this actually work? What does the design of Magentic-One look like if you were to implement this again? So as I talked about before, there's an orchestrator and there's a coder and these terminal, the web server, and the file server. So the orchestrator's job is to implement this complex planning and progress tracking logic. The first thing you see is that when a query comes in, the first thing that the orchestrator does is that it creates a task ledger that we saw before. So it's trying to look up what are the given and verified facts? What are the things that I already know about this particular intent? And then it figures out what it needs to look up. And do I have educated guesses about this already? And how should we plan this? Which agent should do which job? So for instance, here's an example of given and verified that it literally looks like a prompt reflecting on the task and trying to, generate a response. The next thing it creates a progress ledger. So it's trying to think about, are we already done? Maybe this is the orchestrator's internal memory already satisfies the task. Or are we in a loop yet? Are we making progress? Who should be the next speaker and what should be their job? And this is what that ledger could look like. So it's really a structured reflection at this point of the progress of the system. And so for instance, it says, we are making progress and we should choose a web server agent and we need to perform a web search to find the current information about the MSR hack scene. So it's choosing search as the next step that it needs to do. Okay. And so it chooses the web server and the web server says, well, okay, I'm going to go use the browser and try to execute this particular tool. So it goes to a Playwright browser, tries to execute it, fetches the data, gets this multimodal output out of it. And then goes back to the progress ledger. says, are we making progress? Who should be the next speaker? What's the thing they should do? Are we already done? And it says, well, we're making progress. We just did a web search, but we need to visit one of the pages on that web search and then try to summarize information from there. So it's really a loop, and it does so until the task is complete. And so what you really have is an outer slow planning loop, and you have an internal fast progress loop. And there are other things that this, and there are other things that the system can do. So for instance, it's possible that progress is not being made. Maybe the system gets stuck and at some point has to replan. So there's all this logic where it might decide that we've stalled way too many times, and it might decide to replan. Okay, so here's some results from using Magentic-One on challenging agentic benchmarks. On the x-axis you see are 3 benchmarks: Gaia, Assistant Bench, and Web Arena. And on the y-axis you see accuracy or task completion, what fraction of times the agent actually accomplished the task. And you see various baselines here. In Magenta here is the Magentic-One system, and 2 versions of it. One of them is using multiple models for planning. One of them is using the same model. And here in gray is a GPT-4 call, a single GPT-4 call. And what you can see is that performance is quite low. That's basically trying to say these benchmarks are very challenging. You can't solve them with a single LLM call. And then you also see the human performance in light pink here, which shows that people are actually really good at these tasks. And what in green here you see is benchmark specific state-of-the-art agents. So one of the challenges that we see in these agentic benchmark evaluation is that people focus on one of the benchmarks. And so people who have highest results on Web Arena have never evaluated on Gaia or Assistant Bench. And so what you're seeing here is the benchmark specific. And there are open source benchmark specific state-of-the-arts and non-open source. And one of the key results from our observations was that Magentic-One, the very same system, was able to get statistically comparable performance to the benchmark specific state-of-the-art system. So it was really a generalist system in that sense. The same system performed well on multiple benchmarks. One of the interesting questions when we pursue a multi-agent approach is, a question often gets asked is like, why do you need multiple agents? What is the value that each agent is adding to this particular, to the performance? So we did a lot of ablations to understand that. And so on x-axis, what you see is various ablated versions of Magentic-One or M1. So for instance, here on the left, so what you see here on the left is full Magentic-One. Here it's replaced with a simple orchestrator. Here we've minus the web server or the file server or the computer terminal. And what you see here on the y-axis, again, number of tasks that is successfully completed on the validation set. And here on the legend, what you see is the capabilities that task requires to be solved. So this is the metadata that's available in the Gaia data set. And here is the distribution of the full Magentic-One system. So it's solving a lot of tasks that require web browsing, some that require coding. And then here's what happens when you remove the web server from the Magentic-One team. So it only has now these 4 agents instead of 5. The first thing we see is that on the task where human annotators thought that these required web browsing, the performance on those drops. So that sounds pretty natural. If you remove the web serving agent, the performance drops. What you also see is that it doesn't drop to 0. And one of the reasons this happens is because the other agents are able to compensate for this particular web server agent. If you can't browse the web or get information via search, you might try to just use Python to try to solve that task. Here's what happens if you remove the file server from the agent. The tasks that require file handling, the performance on that drops. And there's some potential safety implications of this too. So for instance, remember when the performance did not drop to 0 when we removed the web server from the team? What if you wanted the system to have a preference to never visit a particular website? And you say, well, I'm actually going to go to the web server agent and put a block on what kind of websites it can visit. And now there's a potential path for this particular system to actually still be able to visit that website by writing Python code, for instance, writing GET requests. In fact, we were very, very intentional about assessing these safety issues. So when we were doing these evaluations, we did a lot of things to mitigate this by running these tasks inside containers. We would try to leverage synthetic environments when possible. You really do not want to run this on real Reddit and like create a bunch of posts and like annoy the people. So for instance, we use Web Arena. We deliberately chose models with strong alignment, enabled pre and post generation and filtering. And we also monitored these logs very carefully when we were trying to run these. But at the same time, despite doing all this effort, we saw many, many interesting qualitative observations in these logs while doing experiments. The first was when a benchmark was misconfigured, these agents attempted to do repeated logins, got their account blocked, and then they tried to reset the passwords via an email loop. In another case, they would realize that they're in a synthetic environment, the Web Arena environment, and they were not on the real Reddit. And so they would try to escape that environment and access the real Reddit.com, something we don't want them to do. We don't want them to create new posts on the real Reddit. In other cases, when they couldn't figure out what the answer was, they would try to recruit other people, for instance, authors of textbooks, and try to email them to get the answers for that particular intent. In one case, they started to file a freedom of information request to answer the question. And then many cases, some websites do not want to be crawled. And so they would try to circumvent bot detection by writing and modifying code instead. And there are several implications of these qualitative observations. So for instance, what if somebody created an imposter website of Reddit, a fake Reddit, and used it to socially engineer the agent or inject prompts into it? What could have happened? Could they have gotten this web agent to reveal critical information about the user, maybe their preferences, maybe their credentials, or anything else that might be interesting to the attacker? This Freedom of Information Act request scenario was actually quite interesting. So what happened here was that there was this query from the Gaia dataset, which was basically from the earliest record in the FDIC's failed bank list to 2022. What is the difference between the highest total paid dividend percentage from a Pennsylvania bank and a Virginia bank? Just give the number. And so in order to solve this task, the agents had to pursue a multi-step process, get these numbers, but they got stuck at some point. And so they gave up and instead started crafting this email. And this email basically said, "Dear Freedom of Information Act officer, under the Freedom of Information Act, I'm requesting access to records or available data that contain the following information." And so it started going into this legalese, and there were some very interesting things it started saying in this particular email. It said, "If there are any fees for searching or copying these records, please inform me before you fulfill my request. However, I would also like to request a waiver of all these fees because the disclosure of the requested information is in public interest and will contribute significantly to public's understanding." It also said, "If my request is denied in whole or part, I ask that you justify all deletions by referencing to specific exemptions of the Act. I will also expect you to release all segregable portions of otherwise exempt material." So what this really is speaking to is, if left attended, these agents can do harm. I'm not sure if I'm comfortable with my agents. If this agent had an action in its action space that said, "Send emails on my behalf," it could have sent this very strongly worded email on my behalf. So one of our big lessons from doing this sort of qualitative understanding of the logs was that it's imperative that these agents operate under strict principles of least privilege, and we need maximum oversight while we build them. And we continue to explore exactly this in the next iterations of Magentic-One, and we're focusing a lot of human-in-the-loop planning and oversight. So here's a demo of the Magentic UI system. This was just released last week. Let me see if I can play this. Okay, yeah. So here the task is find me all the papers on human-engine interaction from Sakai 2025. The first thing it does is that it creates a plan. So it starts a co-plan with you. It allows users to refine these intents at low cost. This is to make sure that there's a shared understanding of the process beforehand, before the agents try to invest effort into solving the task, possibly in ways that the user doesn't want, possibly avoid ways. And then it transparently shows the action and the step histories, this co-tasking involved. And then what we see next is, so here's a task where we're asking you to order lunch, crab wonton from this Thai place in Ballard. And another interesting thing it does, in addition to doing co-planning and co-tasking, where it's very transparent about what it's doing, it'll also ask for users' permission before executing any consequential actions. So for instance, here, when it found the crab wonton that it wanted to add to the task, it really asked the user, is it okay if I do this? And the user has the option to approve or reject this. And it does so until the task is complete. And then at the same time, when the time arises where the user should really take control, it gives the user the option to click on this web browser, this embedded live web browser, and take control over it. So for instance, in this case, the user is able to go fill in the credit card information and the address. This way the agent doesn't really need to know about this data. Okay, so in summary, effective task completion is really about evaluating whether the agents will finish the task, will they do the right thing, are they fast enough, was it worth using them? And in the Magentic-One work, we focused more on the accuracy of the task completion, but in more recent work, we're focusing on speed and cost as well, and we're trying to think about how we can leverage fine-tuned small language models to improve to get a better point in this predictive frontier curve. And one of our big sort of learnings that we internalized after this project was that we now have several recommendations on how to correctly and safely evaluate task completion. It's very important to sandbox to make sure your evaluation doesn't cause damage to your evaluation setup, like in our case where agents just got us locked out of the evaluation setup. It's important to use high fidelity benchmarks so that your analysis is producing meaningful results. I think if your web benchmark is very clunky and not high fidelity, I'm not sure if you can trust it as a proxy for real world use. We need to ensure that the agents have kill switch and they have interrupts implemented, and the users always remain in control. And then finally, it's very important to log. I think log everything. These logs actually contain very interesting behaviors and failure modes, which become very interesting research problems. So I want to pause here a little bit and ask for if people have any questions before I shift to the second portion of the talk.
Please go ahead, Martin.
All right, thank you. Thanks, Gagan, for the great introduction there. So the first half of the talk, I'm very interested in the whole setup. So it's very impressive to see what the agents can do and the concept of human in control. I appreciate that. What is your observation on the speed? Is there a native speed of the agents at which they work? Does that need to be decelerated to make sure that humans can still interact, or is it somewhat slow and could it be accelerated? What's your take on this?
So I think there are problems at both end of the spectrum. So like I've seen cases, so many demos that I showed you, they were sped up. And there's a reason, because they are making multiple API calls, and each call has lots of text, lots of observations from tool execution, and they're multimodal. And so it can be quite slow for real-time use. Now, we're a research team and we're building prototypes. When you do product team, they might use a lot of tricks and very high throughput API endpoints to speed that up. But then the other side of the issue where it's very high velocity, that shows up. And I think that is a problem. I use the agent mode in GitHub Copilot quite a bit. And very often when I give it a complex intent, it starts modifying like 5 files. And I have I have to slow down, catch up, go through each file. And they do build in mechanisms in there to, undo and keep each of the edits. But I think adapting the velocity at which these agents act is very important. It's very important to personalize it. And I think that's why we're seeing a lot of research pop up on scalable oversight. So I think it's an open problem, and I think it's personalization also is a big factor there. I think some people are much better at keeping up with the agents than the other. And I think another actually real world examples I've seen about the velocity is the GitHub Copilot for Workspace. So I don't know if you've used this agent in GitHub Copilot for Workspace, but you can go give it a high level task. You go to a GitHub repository, give it a high level task, and I was talking to developers of the system, and they were actually very deliberate in the amount of information that agent would display. And they were very deliberate in showing line by line as the agent is acting. And all of those, it's not the case that it is actually doing things line by line. It has to be that slow. They want to make sure that the developers, it's easy for them to comprehend what the agent's doing in that moment. So I think there's already some products that are doing that, but I think we're going in a direction of advanced reasoning models, even more tool use, agents becoming more complex. So I think we need to keep into mind this velocity argument quite a bit. Yeah.
Thank you.
Okay. Maybe I'll move on if there are no questions. Okay. So, task completion was a lot about, can these agents do the right thing? Can they solve the task? And the question I often think about, do we want these agents to be instruction followers or just instruction followers? We of course want them to follow instructions, or do we want them to collaborators? And my perspective is that we want to go in the latter direction, where these are like amazing collaborators. And so I think this is where thinking about maintaining common ground between agents and people becomes relevant. And there's a seminal work by Herb Clark and Susan Brennan on grounding in communication, where they look at human-human communication, how people collaborate with each other, and what it takes to have successful collaborations. And one of their insights is that successful collaborations require coordinating the content and the process of the goals. It requires people to create shared beliefs about what they're trying to achieve and how they're going to achieve it. So for instance, think about two pianists trying to play four hands. If they want to play that piece successfully, they not just have to know about what they're going to play beforehand, but they also need to be on the same page and have shared understandings while they're playing it. And then many, many insights in this seminal paper, but one of them is that if you look at the dialogue between two people collaborating, you see a lot of intentional effort put into grounding. And you can actually see annotate those grounding acts. So you can see people clarifying things with each other. You can see people following up on other person's response. You can see people that when there's a breakdown in shared understanding or common ground, you see them trying to repair it. So with Omar Sheikh and Eric Horvitz and a bunch of other colleagues, we were looking at what does grounding between people and LLMs look like? And so we started to really think about, are there grounding acts? Can we think about what the grounding acts in a dialogue between ChatGPT and a person and a user looks like? So one of the things Omar did was that he came up with a taxonomy of these grounding acts. And there are three high-level categories of these taxonomies that we came up with. So the first one are advancing grounding acts. So in a dialogue between ChatGPT and a user, you can see these messages, which are all about showing understanding or progress. And then there's another category of messages that you see, which are all about attempting to prevent a misunderstanding. And then there's a third category of messages and dialogue acts, which are all about explicitly signaling misunderstanding between the LLM and the user. And this taxonomy is rich, so you can expand it. You can expand these three categories of responses, and they're actually sorted here in this figure by the severity of the breakdown. So the severity of the breakdown will increase as we go down the table. So advancing acts are all about signaling that there was some progress. So for instance, let's say let's say the question was write a story, or the instruction was write a story. In the next turn, the agent might say, as once upon a time in a mysterious forest. It's trying to further the dialogue. It might acknowledge, it says, I understand, I will write you a story, once upon a time in a mysterious forest. Or it could be a follow-up from the user where, maybe the agent wrote a story, but it says, can you please make it longer? And now they could be ambiguous grounding acts. These could be over responses. So for instance, maybe the agent's confused about or trying to be conservative about how it wants to proceed. So it says, writing a story requires a plan. First, we need to do this. Second, we need to do this. And here's an example story. So it's trying to really understand and be conservative about how it responds. It could be a clarification for the agent. Do you want me to write a story, or do you want me to write a plan to write a story? So these are not really furthering the common ground directly or explicitly. They're kind of doing it. And then these addressing ones, so the ones that are red, they are explicitly showing this lack of common ground. So there's a repair if users indicate repair. So for instance, the agent over responds, the user gets pissed off, says, just give me the story, nothing else. They might reformulate. They might say, the agent has a next turn, and the user says, well, can you please write a story? So they might paraphrase the same query, or they might restart. So this is like the most severe one. This is where we see in the logs evidence that the user just leaves the session and exits. Okay, so what we did, I'm going to quickly walk through what we did to understand grounding in this cases. We took a bunch of data sets that had either conversations between people and LLMs. This is wild chat, which had 55,000 examples. Bing chat, this is from the commercial Bing Copilot that we had access to. And then from multi-was, this is dialogues between people and people, where one of the person is acting as an assistant. And what we did was we said, well, we have these logs. Let's try to figure out a way to annotate them with these grounding acts, because then we can understand to what extent is grounding happening between people and LLMs. So what we did was we took GPT-4o and tried to use it as an annotator based on this taxonomy that we came up with. And of course, before going ahead and doing that, we had to validate that this annotator was going to work well. And so there, the usual trick of computing inter-annotator agreement worked well. So we took people, we asked people to annotate these dialogues with these grounding acts. We asked the LLM to do it, our annotator with the GPT-4o, and then we compare inter-annotator agreement. And that was decently high, so we were able to proceed with doing this. And here's some surprising results that we saw. So once we have all these dialogues annotated, you can think about what are the patterns that are emerging. So what you'll see here are the different data sets that we had. So these two were about human and AI, wild chat, and anonymized version of the Bing Copilot. And then this was multi-was with human-human. So the first thing, what we see is that users have to repair way more with LLM assistance than they have to do with human assistance. So these red bars are high here. This again potentially showing these breakdowns in communication with LLMs as opposed to people. Another result we saw was, again, users have to clarify way more with LLM assistance than with human assistance. Again, these gray bars are much higher when in these human AI data sets than human-human data sets. And then we also see that these LLM assistants over-respond way more than human assistant. This is a very relatable, I think this might be related to many people in the audience, where you see ChatGPT being really verbose about its responses. So we can actually quantify this now with these grounding acts. And then advancing acts, we saw that human assistants ask more follow-ups than LLM assistants. So these green bars are much higher for human assistants than LLM assistants. Again, people are showing way more tendency to try to achieve common ground than current LLM assistants. And then again, we also saw acknowledgements where LLMs over-generate acknowledgements way more than human assistants. So this is another relatable experience where we see ChatGPT saying, well, I really understand it. This is what you're exactly asking for. So in addition to these patterns, one of the interesting things you can do once you have this data set annotated with grounding acts is you can ask what is the probability of a grounding failure at a given point? And so you can ask, so you're basically trying to compute a conditional probability. You're trying to say, well, I'm at this point in my dialogue and I'm about to respond to the user with an LLM inference. What is the chance that there is going to be a grounding failure? What is the chance this conversation is going to go bad? And one of the interesting things we saw from this new data set that we just released was that this probability compounds. Grounding failures compound. So if you see a grounding act, if you see negative grounding early in the dialogue, the probability that you see another more severe grounding failure, that keeps on increasing. And this observation, and so we can empirically quantify this, and this has an interesting corollary, which is that if you could spot poor grounding early on, you could save yourself a lot of effort. And this is, again, a lot of motivation for why maintaining common ground early on is so important, and why do we see, systems like Deep Research and Magentic UI trying to create common ground early on before trying to spend, user time and GPU cycles on trying to solve conflicts. And actually, this space is very complex. So we're talking about human LLM grounding here, but in this recent work with Jen Morton-Wan and Dan Malt, we were looking at human agent grounding and trying to look at what happens, what are the key challenges in trying to maintain common ground with people agents. So there were three big types of challenges that we saw, and they were related to the direction of information. So there's challenges related to how to give information from the human to the agent, others from the agent to the human, and there's a bunch of cross-cutting challenges. And all of these challenges that we talk about, they're focused on two key changes. The first is multi-step reasoning because of these new LLMs, and also tool use. So I'm going to quickly go over what these challenges are. So for instance, here are the challenges in conveying information from the user to the agent. What should the agents achieve? Which preferences should the agent respect? What should the agent do differently next time? And they're all spread across on the x-axis in the phase of before, during execution, and after the execution. There are other challenges which have to do with conveying information from an agent to the user. What can the agent do? What is the agent about to do? What is the agent currently doing? Were there any side effects or changes to the environment? And was the goal achieved? So I know I'm going very quickly over these questions, but in the demos that I showed you and some of the things I showed you, you might have seen glimpses of some of these questions being gradually addressed. And there's several cross-cutting challenges here. So for instance, how should the agent help the human verify its behavior? And you can apply X1 to many of these other challenges here. How should the agent convey consistent behavior? This is particularly important because many of these LLM and agentic systems tend to be stochastic. How to choose the appropriate level of details. If you've been working on explainable AI, I think you can realize the importance of this particular issue. Which past interactions should you consider when communicating? This is where I think personalization and explainable AI come in again. Okay, in summary, this problem about common ground is human agent interaction is because human agent interaction has become very complex and dialogue oriented, and creating shared understanding about content and process is important. I think I don't have very much time left, and I did have a third portion of the talk. I'm going to just quickly go over it in 1 minute. So this last issue was about auditing agent behavior. And a key problem here was how the heck do you build a multi-agent system? How do you debug it? And what Will Epperson, one of my interns last year, did was that he said, let's try to build tools to help users and developers figure out what went wrong. And so one of the things he did was that he built this amazing interface called AG Explore. It let people ask counterfactual questions about agent behavior. This is in attempts to debug it. And he saw interesting behaviors in his qualitative studies where counterfactuals helped developers figure out alternate where exactly to go and make an edit in the system to get it to do the right thing. Here's some work by Grace Probsting on automated log analysis. So again, really long logs, you want to figure out, pinpoint where the errors is. So we started thinking about this particular problem just like linting. So if you're programming, you probably know about linting. We're trying to do static analysis to figure out where the bugs might be before we execute the code. Same idea here. You're not trying to execute the agents to figure out where they went wrong. And so you're looking at the logs, trying to pinpoint errors. And so we have this tool in AutoGen Bench, the evaluation framework that we use, where you can point it to a log and it'll tell you which lines and which messages in this log look problematic and demand users, the developers or the researchers' attention. And we use this postmortem tool to do automatic log analysis in Magentic-One. It helped us figure out that one of the big issues with Magentic-One right now is that there's persistent inefficient actions, which means it fails at something but retries the same thing. It fails at it again and tries it again. There's some work by Peter Saihan on measuring autonomy. So this work is really about assessing the impact of the action spaces of these models and looking at the impact on the environment or the impact. And so he there developed a taxonomy. It's trying to do code inspection and look at what sort of impact, what level of impact it could have. And this is a way of quantifying the degree of autonomy of these agents. And there's other prior work we've tried to do on auditing interaction between people and GitHub Copilot that you might be aware of. One big insight that came from this work was that we found empirically that programmers were spending about 25% of their time just double checking the ghost stacks that these copilots explain. So yeah, auditing agent behavior is really about trying to figure out where the heck they went wrong and like how we can do fix it. Okay, so to conclude, it's become much, much easier to create goal-based agents with LLMs that can use these reasoning models and use tools. And there are several challenges to make them useful to people in the real world. We need to make sure that they can complete tasks effectively. So we need to measure their task completion and if they're effective, otherwise this bottlenecks progress. We need to find ways to maintain common ground between people and these agents. And there's a very rich space of challenges here. We need to figure out or audit the level of autonomy, the failures that these agents have using scalable approaches so that we can improve them. And I think evaluations focused on these areas really can help understand impact on people and create genuine human-centered agents. We released lots of open source tools. We really believe in open science in AI Frontiers and in MSR. And we released so many open source tools that have amazing traction in the community. So if you're working on human agent interaction, chances are that some of the problems that you're working on, we might have already open sourced it and maintained a good repository. So please check out these repositories. And there are lots of articles we published as well. So please check them out. With that, I'm happy to take any questions.
Thank you so much, Gagan. I think I see already hands up. Chirag, you're next.
Thanks. Hey, Gagan, welcome. Good to see you here. My first question, which you don't have to answer, is how are you able to use MacBook at Microsoft? But don't answer that. We can talk it offline. The question I wanted to ask is, and this is what I've been seeing in a lot of work when we use these benchmarks, and I feel like they're just really not right benchmark for the kind of agents that we envision. So on one hand, we envision these agents that are doing very user-oriented, interactive, complex tasks, and then we are using, and I really mean we, because I'm included in that too, benchmarks that are really not designed for doing that. I mean, they're kind of very static. They're very rigid. And they measure some aspect of agents' capability, but not the interesting aspect. And so should we develop new benchmarks? Should we just abandon benchmarks? I mean, are there other ways, like more fundamentally when it comes to evaluation, right? And that's a challenge currently that we face. And I think we're going to face even bigger challenges as we have to think about, not just grounding, but also alignment issues. Right? So I just wanted to hear your thoughts on that.
Yeah, I think my perspective is that in an ideal world, I would be able to make a change to my agents or whatever complex system I have, and magically from a set of users be able to assess what the impact on the users is without causing them any harm, without spending many dollars on it, without spending 2 weeks trying to get those results in an ideal world, but that's not going to happen. So I think what ends up happening is that I do need to make incremental changes to my agent or test many things. And so I think benchmarks become a necessary evil. They have their limitations, and I need the results fast. So, but we know there are limitations, so we can't stop there. So I think to me, I almost think of benchmarks as unit tests. We made a change to a prompt. We added a new tool. Maybe we, changed some other portion of the code. And I want to quickly know, did this result in a complete breakdown? Did this result in a big blunder? So I think benchmarks are really useful for that. But you're absolutely right. They are not enough. And this is one of the reasons that if you look at Magentic UI, the demo that I showed you and that we just released, we've been doing lots of user studies and deployment studies with that. And this is, we just want to know if something broke while we were trying to make any changes to it. For instance, let's say we added collaborative planning logic to it. Is it became the case that one change dropped the performance on the Gaia benchmark with 30%? If that happens, we want to know there's a bug in there that happened, but we don't want to stop there. So I think benchmarks are a necessary evil. We need to start. We need them, and we need better benchmarks. But I think we should not stop there. Or at least that's the approach we're pursuing here.
I think it's a longer conversation. Yeah, absolutely. But thanks. Yeah, I agree with you. Yeah, it's necessary, not sufficient.
Yes. Yeah.
I'll ask a quick one since I don't see any hands. You talk about, firstly, a great talk. You mentioned about humans, and I just wanted to know from your perspective, like when you say humans, like what are you referring to? Because especially, the task that you were showing, the Magentic AI demo, this goes back to the previous question during the talk, where it seems like if the user is a developer, they can actually has the ability to kind of get into the planning and correct few things. But for a regular user who's not a developer, this is like almost impossible. And you also said like it's difficult for you as well, being the developer of these systems. I'm wondering, like, what do you consider in terms of user? Is a taxonomy of users that you're thinking about as you're designing these systems?
So with Magentic UI, actually the audience is lay users. There's a reason that we very carefully picked web automation as our domain, because that's something everybody does, as opposed to more specific domains like healthcare agents or research agents. And actually, when we did user studies with end users here, and there was a bias there. They were tech users, they were Microsoft researchers, not from the team, but rest of the Microsoft. It was actually pretty easy for them to get started and onboarded to using the system, to collaboratively plan. There was a lot of diversity in how they collaboratively plan. For instance, some people want to go and edit that plan. Other people don't want to edit it. They don't want to reorganize the bullet. They just want to give natural language feedback because editing is too complex for them. But I don't think I ever saw a case where people were like, I don't feel good about giving it feedback on the plan. But again, there's a bias here that these were tech-oriented or tech-literate people. I don't know if my dad would be able to do it. So you're absolutely right here. We had a bias here for tech-literate people. And I think it was a starting step for us. But you're absolutely right. We need to do more research on making these agentic systems accessible and keeping those user requirements in mind during the development of these. And sort of my perspective is that this was a good starting point, a decent starting point for us. But absolutely, I think this is why we need collaboration between people in academia, why we open source everything. And if some student wants to fix this up and wants to go ahead and show that this doesn't work with lay users and wants to optimize it for it, it's open source. Yeah.
Thank you so much. I know we are actually completely out of time, and then there are 2 more hands, but I want to be respectful of Gagan's time. So please, if you have questions, I believe, Gagan, your email is up there. And so, please reach out with that. Thank you for spending time today with giving this really thought-provoking talk. Thank you, everyone, for attending, and see you all next week.
Thank you for inviting me. very much. Please email me with questions or reach out on Twitter or something. Yeah,
Thank you very much.
thanks.
Have a good one.
Wait, what's your email?
First name, last name at Microsoft.com.
Okay, thank you so much.
Thank you.